Perfect. Okay, so our next speaker is Nava Gaddam, who will tell us about page curve and emergence of theorems from black hole scattering. Please.
Thank you, Marcus. Thank you to all the organizers for having me speak here and for all of you for being here. I'll talk about somewhat of an old-fashioned way of looking at black holes, perhaps something that should have and could have been done 50 years ago, but somehow interesting things seem to emerge despite the old-fashioned nature of the problem. So this talk is based on a couple of papers that I wrote last year with a very talented PhD student here in Utrecht, Nico Groeneboom, and Gerard Hoofd, who's also in Utrecht and doesn't need an introduction to this audience, and also some work that's hopefully going to appear soon. Soon. So I want to start with something that's very familiar. So I'll have a quick look at the information loss problem for black holes, something that Hawking formulated, where he considered scalar fields that are propagating freely on a black hole background. And he drew this diagram in Eddington-Finkelstein coordinates. So what you see is infalling matter that's collapsing into a black hole, and then that radiates particles which reach Scri plus at future infinity. And Hawking argued that if you look at modes that are received at Scri plus and you trace them all the way back, that the free field theory should be good enough to capture these effects as long as you ignore Planckian physics. He traced them all the way back to the Cauchy slices on Scri minus on past null infinity. And he found that the modes are related by some thermal prefactors, and that therefore you would lose information regardless of what went into the black hole. This was slightly reformulated by Page in the following sense. He argued that the entropy of the black hole was known to be given by the size of the black hole. But he said that an interesting quantity to look at would be the entanglement entropy of the radiation itself that's received. As soon as the black hole is formed, there's no radiation, so there is no entanglement entropy. But as the black hole starts to evaporate, this entropy of the radiation starts to increase. And he argued that the Hawking entropy suggests, or information loss suggests, that this entropy continues to grow until the black hole completely evaporates. But if unitarity has to be true, then the curve should turn down at some point. And the characteristic time scale at which this curve turns down is associated with the lifetime of the black hole, or sometimes called the Page time. So what I want to argue today is, this is something that's very well known, that gravitational interactions at some point should play a role. And the question is when. So if you consider two particles that are scattering, so that are gravitationally interacting, it is known that if you have highly energetic particles that collide at small enough impact parameters, the scales are of course extremely important. I'll define all the scales and I'll say what I mean by small enough and what you compare with. But for now, if impact parameters are small enough, then black holes should form. And therefore, you cannot ignore gravitational interactions. So the question is there a regime of phase space where amplitudes are calculable in effective field theory? The first question, of course, is why would such a regime exist? Or why would we expect such a regime to exist? And the reason is that there are a couple of reasons. One of them is that, firstly, the information paradox is a problem for large black holes. So you expect that it can be resolved in some version of an effective field theory. For all of you who followed the island proposals and so on, there are a lot of indications that this is indeed true, that we expect this problem to be resolved in effective field theory. Another thing that one could note is that gravity is sort of special in the sense that quantum effects arise not only from large momentum transfer, like in quantum field theory, but also from emergent scales, like the Schwarzschild radius. That's, in some sense, one would have said this already when the information paradox was formulated, that there are emergent quantum properties associated to black holes in effective field theory already. So what I hope to do in this talk is to define this regime in effective field theory. I'll sketch the calculation of some amplitudes, and I'll tell you how page time emerges naturally from some of these amplitudes. And I'll sketch certain additional applications in this regime of phase space using these amplitudes. The punchline is that there are many applications actually. The one that I might, time permitting, that I might focus on is emergent soft theorems near the horizon. So here's the plan for my talk. First, I'll recap in some detail gravitational scattering in flat space so that it allows me to go to the black hole case relatively easily. And then I'll talk about the time delays and emergent theorems. So let's start with the flat space scattering picture. So what I have in mind is the Einstein-Hilbert term coupled minimally to a scalar field, and I want to perturb the metric in the weak field approximation. So you have eta mu nu plus h mu nu. There are interactions that are generated by a 3-vertex where the graviton couples to the stress tensor. And of course, the metric written as a tensor, a symmetric tensor has too many degrees of freedom. So one has to fix gauge when computing any physical quantities. So the one that's often employed is the covariant gauge or the Dondra gauge. So it's known, and there are lots of nice papers in this topic. Some of those I list at the right top of your screens, where if you focus on the regime where the Mandelstam variable S dominates the momentum transfer effects T, then the diagrams that are leading when the energy of scattering, the scattering energies are trans-Planckian, are the so-called ladder diagrams, which look like drawn. So the first one is the tree level diagram, the next is a one loop diagram. Remember that I'm only looking at diagrams that are generated by the 3-vertex, so there are no gravitational self-interactions yet. They can be added. And then there are 6 two-loop diagrams and so on. What's remarkable is that in this phase, all these so-called ladder diagrams can be resummed perturbatively exactly, and the amplitude can be written down. Here's an expression for what that amplitude looks like. All the quantities here are what I already told you about. So there's G Newton, there's the Mandelstam variable. Because momentum transfer effects are so low, the effects are dominated by soft gravitons, meaning that the virtual gravitons that are exchanged have zero momentum or very low momentum. That means that in the propagators, you need an infrared regulator because the graviton is massless. And this amplitude can be written in terms of one function, which is often called the eikonal function. That's chi, that's written at the right bottom corner, where B is the impact parameter. So it's the length, it's the distance between particles. One way to think of this amplitude is think of 2 particles that are scattering in flat space at distances that are extremely large from each other. So on the Penrose diagram, they look like they're crossing each other, but in the transverse plane, they're very far apart. And this amplitude essentially captures the shock wave, the Eichelberg-Sechsel shock wave in flat space. So here are some amplitudes that you can compute to all loops in this regime. So the natural question now is where are the black holes in the game? When impact parameters B reach the emergent scale in the problem, because G Newton is dimension full, the moment you have some energy of scattering, you can construct a length scale, which is G Newton times this energy. The statement, what is known is that when impact parameters reach that scale, the emergent scale associated to the scattering, then the eikonal amplitudes that I just drew start to diverge. And this suggests that there's some new state that's being produced that's not captured by just perturbations from flat space. And these are this is where black holes are expected to appear. That's another way of saying that gravity is special, that there are emergent scales which play a role already in somewhat of an effective sense in effective field theory where quantum effects show up. Before we go to black holes, what was actually very an interesting set of developments that occurred there after the eikonal amplitudes were studied were to consider stringy corrections to these amplitudes. So as I said, let's call the emergent scale G Newton times square root of S the Schwarzschild radius associated with the scattering problem. And there are, if you include string theory, there's 3 length scales in the problem. There's the impact parameter, there's the Schwarzschild radius associated to the scattering, and the string length. The eikonal regime that I just talked about is when the impact parameter is much bigger than the Schwarzschild radius and also the string length. These can, of course, be corrected perturbatively by RS over B or string length over B corrections. So those diagrams, if you wanted to look at it visually, would look like the following. So the H diagram would be a classical correction arising from RS over B. The vertex corrections would look like quantum corrections that are emerging from string length over B. Another regime is where the string length dominates the Schwarzschild radius. So this is the statement that if you're trying to reduce your impact parameters from the large to small, that before you produce black holes, that you produce string states. It's an interesting regime because you can avoid or you can hide classical black hole production under the rug, and you start focusing on production of stringy states. This is something that can be, that's interesting. It's been studied by Amati, Ciafaloni, Veneziano, and a lot of others thereafter. What was already noticed there is that now after you study these amplitudes, if you send your string length to approach the Schwarzschild radius, that already there's some black hole-like behavior in the amplitudes, namely that the final momenta, the external states, go with 1 over the size of the black hole, which is what you'd expect for Hawking radiation, for instance. What's interesting about studying these stringy effects is that the Schwarzschild radius and the string length can be tuned with respect to each other, one to be made very small or the other to be made very small by tuning G string. This goes under the name of the black hole string transition. The third regime, which is actually of interest for classical black holes, is where impact parameters are roughly of the order of the Schwarzschild radius or smaller. But to stay in effective field theory, you want the impact parameters to still be much bigger than Planck scale. This is what I want to focus today. And again, you can tune G string when you incorporate stringy effects and capture black hole string transitions. So what I want to do now is to explain to you what I mean by black hole scattering. Now you can generalize what was known so far for flat space to black holes. But let me pause for a second to see if there are questions.
Maybe one small question. So in the beginning, you said you expect effective field theories to still apply. Maybe one sort of lesson, I guess, from like lots of the developments also with wormholes is that I guess you sort of expect some sort of non-locality to come in. So is the idea here that sort of the non-locality is played like by a string?
So the question is, so far in everything that I'm going to say, there's no non-locality yet. So the question is, one has to define what observables that will have non-local effects showing up. And in all the scattering amplitudes that I'm going to talk about, there is no effect of non-locality. The effective field theory is just perfectly local. Of course, at some stage, these should appear. And as you say, perhaps, yeah, the question is, do you expect this to appear only at the string scale or already below? Okay. So in contrast to the flat space eikonal, the phase space regime that I'm interested in now is where the impact parameters are much bigger than Planck scale, but are of the order of the emergent Schwarzschild radius or less. And correspondingly, the energies that are relevant will now be such that energy times m black hole is now much bigger than Planck mass squared. Whereas remember that in the flat space eikonal, energies had to be much bigger than Planck mass. So because of the size of the black hole, the collision energies can be very small, and the diagrams that we drew like before would still be dominant near a black hole. So the range of parameters for which the calculations are valid, or this effective description is valid, is actually much wider than you would expect in flat space. So the scattering problem now is to perturb on top of a black hole background. So we have, again, a background field expansion, and I'm going to look at scattering amplitudes that are mediated by the same 3 vertex. But the problem is now that because the black hole metric is more complicated, the canonical gauge, firstly, solving even the Klein-Gordon equation analytically, so inverting the propagator for a scalar field is not known analytically. So one would like to exploit spherical symmetry of the solution. But the trouble is that the Redonder gauge couples all the different harmonics, the spherical waves or partial waves. So one is to use a clever gauge. And Regé and Wheeler in 1957 wrote a nice paper where they invented such a gauge. And that gauge looks like the equation that you see on the right top, or to the right of your screens, where it's split into an even mode and an odd mode. HAB is a symmetric tensor, which runs on the light cone coordinates or the conformal coordinates. So that has 3 components, and K is a scalar that has a 4th component on the transverse sphere. X has 2 components that sits in the odd mode. So in total, you make up your 6 degrees of freedom that are off shell. Once you write your metric perturbations in this gauge, you can expand them in partial waves. The tensorial harmonics are slightly more complicated than the scalar field spherical harmonics, but one can show that all this harmonics decouple because the solution is slightly symmetric. And one can also show that as long as momenta on the transverse directions are small, that the odd parity graviton does not contribute. So you can now write an effective theory, which is an infinite set, like a Kaluza-Klein tower, an infinite set of 2D effective theories, one for each partial wave. And so the way to define this phase now, just to recap what various things that I said over the last few minutes, is that there's a separation of longitudinal and transverse effects. This is a statement that the background is slightly symmetric, so the different partial waves don't mix. Of course, interactions will change that slightly. The impact parameter, we want it to be small. So one way to achieve that is to take your particles and scatter them near the horizon, so that the distance between them on the transverse sphere can be at best the size of the horizon, so they can be smaller. And now, as I said, the emergent scale of the size of the black hole now comes to the rescue, where collision energies can be much smaller and not necessarily Transplanckian, in contrast to the flat space eikonal. So one can write down in the near horizon region, one can write down the Feynman rules. There's a familiar scalar field propagator where there's in 2D, there's an effective mass that comes from the partial waves. And the graviton propagator can also be written down. Remember that this is only in the near horizon region. I haven't solved anything here. I've just inverted the operators in the near horizon region. There are expected UV divergences that sit in the sum over the partial waves. But the nice thing is that because of the size of the horizon, the theory is infrared regulated, in the sense that at zero momentum, the propagator does not blow up. And the vertex, the interactions are mediated by an emergent coupling constant, which is now m Planck over m black hole. So this theory, this perturbation series makes sense as long as the black hole is very large. This is the analog of the weak field approximation in flat space. There are some additional gauge subtleties for the monopole and the dipole, so L equals 0 and L equals 1 modes, that I'm glossing over here, but we can talk about it if there are questions. So using this toolbox, you can now compute elastic 2-to-2 amplitudes. These would be the analogs of the ladder diagrams that I drew earlier. And one can compute, again, the resummation of the amplitude, and that for every partial wave, and that can be written as an exponential of this black hole eikonal function now, which looks like g Newton times E squared. E is the energy of the collisions, divided by L squared plus L plus 2. Now, if you write the same amplitude for the flat space eikonal, there you see that the L squares, the partial waves, sit in the numerator. So the amplitudes are dominated by large angular momentum modes in flat space, whereas once you're near a black hole, the amplitudes are now dominated by the small angular momentum modes. It's an interesting physical difference that's important to note. And just as with the flat space eikonal, where the eikonal function was defining for us shock waves in flat space, one can show that the black hole eikonal also captures the Dreyerhof shock wave, which is now a shock wave on the black hole spacetime. This is also related to the Stanford-Schenker eikonalization in ADS, because the asymptotic physics does not play a role as long as you're looking at the near horizon dynamics. Good. So now now that we have this toolbox, you can ask more general questions. What happens to particle production, for instance? So can I compute 2 to n amplitudes? I'm still in the same regime of phase space, where we're now computing the amplitude of 2 particles falling into a black hole, and instead of 2 of them emerging, an arbitrary number of them emerging from the other side, some arbitrary n. At tree level, one finds that this amplitude is given by the expression that you see here, where tree level you expect that because of the number of vertices that you have, you expect a coupling constant raised to n, and you see that there's an interesting coupling constant that is emergent near the black hole. And this tree level amplitude was found by arguments that there's a new classicalization owing to the presence of black holes already in flat space that was argued in this nice paper by Dwali and co. And we find that this effective field theory captures exactly the same physics, and you can write down the same tree level amplitudes using the Feynman rules that I wrote down earlier. And you can work out that this amplitude is sharply peaked around some maximum value of n, which is given by E squared times G. And Dwali and co argued that this E has to be also, it's also dominant when the energy of collision itself is also the size of the black hole. And they said that this gives you a relation that you expect, which is that the number of particles that emerge, or this number operator, is goes with the entropy of the black hole.
You have 5 minutes now.
Yes, thanks. So one would like, now that we have the effective theory, you could compute additional diagrams. This is just a tree-level diagram that I wrote down here. So the general diagram would look something like a cobweb, where there are virtual graviton legs that are all over the place. This is a very difficult diagram to compute, but this might be actually very interesting to understand endpoint iconalization, because from the 2 to 2 amplitude, from the 4-point function, there's the Lyapunov exponent that shows up and gives you a chaos bound, where now one could ask, is there like an endpoint analog of this chaos bound? Are there higher moment chaos exponents that show up for different ends, or is the 4-point amplitude somehow special? So are there any universal additional constants that are of importance? But unfortunately, these are difficult to compute. But what we found that we could compute is a diagram that I like to call the ladder of ladders. So this is like a chain of different ladders, or a ladder of multiple ladders, and an explicit amplitude can be written down. Remember that this amplitude is not necessarily indicative of anything. It's just that one could write it down, because we don't know if these infinite sets of corrections are actually dominant for any problem. There are additional diagrams that also contribute. But what I wanted to illustrate with this expression is just that certain amplitudes can be written down, and the effective field theory is good for more things than I'm able to show right now. So much for a statement about the diagrams themselves and what can be computed, what the scattering problem is. I move on to time delays, or where does page time come into the picture. Every time you have a scattering problem in quantum mechanics already, there's an interesting notion of time delay. And the statement is that if you throw a particle into some potential, how long do you have to wait before you receive the wave function back? The more complicated the potential, the longer you probably have to wait. But is there a way to estimate this thing? This was studied by Eisenbud-Wigner in the 30s already. So the argument goes as follows, or the way to define this time delay goes as follows. Consider an S matrix near some resonance, can always be written as some slowly varying function because you're near a resonance, divided by E0 minus IE minus E, where this resonance has some width E. The time delay is a quantity that's defined as the derivative of the log of S, or the imaginary part of it. The way to understand this is that if you evaluate this thing for the S matrix that's written in the first line, this looks like E over E minus E naught squared. And if you go to the resonance, it gives you the lifetime of the resonance. So the statement is that if you have some scattering problem, some intermediate state forms, and you compute this time delay quantity, it gives you how long this intermediate state lives for. So let's apply this thing to the black hole scattering matrix elements that we just computed. For the elastic scattering, if you plug this formula in, you get that the time delay is m log m. This is what is called the scrambling time. And if you try to compute the same thing for the 2 to n scattering amplitude, it gives you g squared times m cubed. One has to slightly generalize the formula that I wrote on the previous page, because now you have inelastic scattering with many different channels. But this can be easily computed. We wrote it in this paper this year. So what you find is that the elastic amplitude captures scrambling time, whereas the particle production amplitude, the large n amplitude, captures page time, or half the lifetime of the black hole. So the way I interpret this result is that Hawking's free field theory breaks down after page time. The reason is that we threw two particles that are highly energetic into a black hole. For the longest time, for the initial half of the lifetime of the black hole, these particles just stay there and you receive Hawking radiation. But after half the lifetime of the black hole, or g squared times m cubed worth of time, you see that information that you threw in is re-emerging. So after page time, if you continue to treat the problem as a free field theory, then you miss out on this information. So the free field approximation breaks down after a while. And that's very nice to see from the amplitudes that you can compute. And so far, all the physics that I've computed is just local stuff. Of course, the scattering matrix itself is something that maps asymptotic states to asymptotic states. In the last minute, I'll tell you about Emergent soft theorem. So perhaps all of you have seen this Weinberg soft theorems in flat space. It's a statement that if you have m to n amplitude, or the way I drew it here, n to m amplitudes, and you add an extra soft particle in, that near the soft, if you perform an expansion near the small q expansion, where q is the momentum of the external graviton that you added, that there are two dominant diagrams, and this gives you a relation between the amplitude without the external graviton that's on the right-hand side of the equation M, and the amplitude with the external soft graviton. And the leading term in the small q expansion is the leading soft graviton theorem. Over the last 8 years or so, there's been a lot of development where people try to relate, or people found that these are directly the same as the wadded entities corresponding to infinite dimensional symmetries near future infinity or past infinity, the so-called BMS symmetries. But now that we have a scattering problem that seems to be well-defined near the horizon, you can ask whether you can compute a similar relation near the horizon. And there seems to be an emergent soft theorem with exactly the same logic, where now the coupling constant is now given by m Planck over m black hole for every partial wave, instead of G Newton that was in the flat space regime. It's something that should hopefully appear soon. But we're trying to explore now whether, and it seems most likely the case, that these amplitudes are related directly to the near horizon infinite dimensional symmetries that were also known to exist. There's probably a lot more to be said about this. And hopefully this will be developed in the near future. So let me conclude. What should you take away from what I said so far? So there seems to be a remarkable new phase of quantum gravity that captures black hole evolution. The information paradox is apparently addressed in this phase, and there's no UV completion needed for this specific problem. There are also emergent soft theorems near the horizon that are different but akin to Weinberg's flat space soft theorems that seem to emerge. There's probably a lot more to be explored. Here are a bunch of ideas that one can consider. With that, let me thank you for your attention.
Thanks a lot, Nava.
Thank you.
So are there any questions? Maybe I right away start with one. So
Sure.
You're doing the calculation in the near horizon limit of a Schwarzschild black hole. So sometimes if you go to the near horizon limit of an extremal charged black hole, for example, this becomes ADS times S, right?
Mm-hmm.
And you might expect maybe you can do a scattering or you can relate the scattering amplitude calculations to some ADS times S, where the extremal or the mass parameters, the parameters of the black hole are associated to something like the negative cosmological constant of the ADS or the radius of the sphere.
Mm-hmm.
Does that make so do you think that this can be used in order to explore more regimes and like backgrounds of charged black holes? Or
so for charged black holes in general, I see no trouble. For adding a cosmological constant, I see no trouble. Actually, the calculations are almost identical, because you see the dominant part was the zero momentum graviton. So you just need the propagator of the graviton at zero momentum. If you add a cosmological constant, you just generate a contact term. So that will change this constant somehow. But the results and the exponentiation, a lot of results should carry through. The trouble, though, is that if you take the elastic amplitude, this is related to the shock wave. Already the shock wave is not very well defined for extremal black holes. The coordinate transformation that one needs to write down a shock wave solution for extremal black holes, that is singular. So I'm not sure how much of it carries forward and how much is hard.
I see. Lars.
Yeah, I think it's a really nice talk. I had a question about sort of the definition of the S matrix. So because you're dynamical gravity, and normally it's very difficult to define like observables that are diffeomorphism invariant. Like you need to do some relational dressing and everything. So when you're thinking about this S matrix, do you have in mind that you sort of the asymptotic states that you're considering have some like take this into account, or is it not necessary to do that?
So far, what I see is that so the standard way people try to address this, and Giddings and Subrat Raju have had a lot to say about this in various contexts. The way people try to address this is that indeed, when you consider certain if you to define observables that are gauge invariant, you need to dress them, and then when you dress them, non-local effects appear. The dressed operators are no longer local. So far, I haven't had to encounter this anywhere. The amplitudes that I'm considering are very similar to what you would do. I mean, none of the calculations that I'm doing are very non-standard, in the sense that if you were to compute amplitudes for charged particles in the background of a large electromagnetic field, you would do something similar. You have E plus E minus that's interacting with some perturbations over some gauge field. So my impression is that all the non-local effects should appear, but then they don't yet appear at the level in which I'm computing things. So one has to define probably slightly more refined observables to be able to see these effects and to say something. It's useful to say that I've ignored certain effects that arise from transverse effects because I assume transverse momenta to be small. And this is where I expect additional ultraviolet-like effects showing up. And I threw them away because they were subdominant in the regime that I looked at, where E times M black hole is much bigger than Planck mass squared. But there's nothing stopping you from perturbatively looking at these corrections and analyzing them in more detail. It might be that these corrections do not exponentiate and you may not be able to resum all the ladder diagrams or the analog to the ladder diagrams. But one loop, two loop, one can probably study these, or one can certainly study these because these are simple diagrams that can be calculated. And I expect a lot of these effects to show up there.
Okay, thanks. That's